Lecture 2-3 AC Circuit Analysis, KVL and KCL. You should be reading sections 9.3 and 9.4 in your textbook to supplement this lecture. The learning objectives for today include the following. Students should be able to apply KVL and KCL to sinusoidal steady state circuits in order to solve for voltages and currents. The application of Kirchhoff's current law is the same in the frequency domain as in the time domain. It states that the sum of the currents into and out of a node is equal to 0. Another way of stating that is that current in equals current out. Recall that a node is the point where two or more circuit elements meet. So the following network actually has two nodes. By summing the currents into and out of that top node, we would have that the current out, I1 plus I2 plus I3, equals the current in, which is IS. The application of Kirchhoff's voltage law is the same in the frequency domain as it is in the time domain as well. It states that the sum of the voltages around a loop is equal to 0. Another way of stating that is that voltage rises equal voltage drops. Recall that a loop is where a trace of elements is connected with no node or element being included more than once. So for this single loop circuit, we would have that our voltage rises, V1 plus V2 plus V3 equals our voltage drop, which is Vs. That if you do a clockwise loop, or if you do counterclockwise, you would have the voltage rise, Vs, equals the voltage drops, V1 plus V2 plus V3. Now let's try an example. Use a phasor diagram to find the following sum. 3 plus J4 plus 8 minus J plus -1 minus J3. We will illustrate with the phasor diagram that when you add these up, you get the real part is 3 plus 8 minus 1, which is 10, and the imaginary part is 4 minus 1 minus 3, which is 0, so that this sum equals 10. So the first thing we're going to do is to draw a phasor diagram. Remember, the horizontal axis is the real axis and the vertical axis is the imaginary axis. So next I'm going to sketch the vector 3 plus J4, and then I am going to add to that my next vector, which is 8 minus J. And then to the end of that, I'm going to add the vector -1 minus J3 and show that the final result is a vector along the real axis that is 10. All right, let's try another example. Use KVL to determine the phasor current and voltage across each element in the following diagram. Express all answers as phasors and in the time domain and draw the phasor diagram. We're going to express our answers in terms of volts RMS, which means that if our source is the square root of 2 times 10 cosine 40,000 t, then VRMS is 10 volts RMS, and our angular frequency would be 40,000 radians per second. The first thing we're going to do is to find the impedance of the inductor, which is J times 40K times 225 micro. So the impedance of the inductor is J, 9 ohms. Then we're going to find the impedance of the capacitor, which is -J over omega C, or -J over 40K times 5 micro. And we get that the impedance of the capacitor is -J, 5 ohms. So we already were given the circuit drawn in the time domain. So in order to do our AC or phasor analysis, we have to redraw the circuit in the frequency domain. So that means we write the source as a phasor and the elements as impedances. So we're going to write the source as 10 angle 0 degrees in volts, and that's RMS. The resistor is the same impedance in the time and frequency domain, so that's 3 ohms. The inductor is J9 ohms, and the capacitor is negative J5 ohms. Note that we will have Vs equal the voltage across the voltage source, and that should equal, based upon Kirchhoff's voltage law, the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor. So now if we label a clockwise current I is equal to V over Z. So we're going to have 10 with an angle of 0 degrees over 3 plus J9 minus J5. And this yields a current of 2 with an angle of negative 53 degrees. So the voltage across the resistor should be 3 times I, or 6 with an angle of negative 53 degrees. In the rectangular form, that would be 3.6 minus J 4.8 volts. The voltage across the inductor should be I times J9. Or, using the voltage divider, you can also find it by doing J9 over 3 plus J4 times 10, which yields 18 with an angle of 36.87 degrees. In polar form, or in rectangular form, 14.14 plus J, 10.8 volts. Next, we'll find the voltage across the capacitor. Using the voltage divider, that's negative J5 over 3 plus J4 times 10. So the voltage across the capacitor is 10 with an angle of negative 143 degrees, or in rectangular form, negative 8 minus J6 volts. In the time domain, the voltage across the resistor would be 6 cosine 40,000 T minus 53 degrees. The voltage across the inductor would be 18 cosine 40,000 T plus 36.87 degrees. And the voltage across the capacitor would be 10 cosine 40,000 T minus 143 degrees. So next we will confirm KVL with a phasor diagram. So we're going to put VR, VL, and VC on our phasor diagram and show that when we add those all up, they sum to the source voltage VS. So the first vector that I will draw is the voltage across the inductor, and that makes an angle of 36.87 degrees with the real axis and has a length of 18. Next, I will draw the voltage across the resistor, and we see that that makes an angle of negative 53 degrees with the horizontal and has a length of 6. And then finally, I will draw the voltage across the capacitor, and we see that that makes an angle with the horizontal of negative 143 degrees, and it has a length of 10. Notice this may not be totally to scale. And after I sum all of those up, then this should yield the voltage across the source, which is labeled here. as 10 with an angle of 0 degrees. And this concludes today's lecture on using KVL and KCL to solve AC circuits. Please come back for more.